So first off, let's start off with questions about 6.2. Anybody? I was looking through it this morning, and the third question dealt with the variance pretty explicitly. And I noticed in the view an example for number 3, it mixes the shortcut and the long formula, which, you know, you can use one or the other. It doesn't matter which one.
Can we go over either 2 or 3?
Yeah, sure. See, I was looking at 3 this morning, and in the view and example, it had a little typo. Where's it at? When it's finding the variance of the population right here, it has the formula where it's the sum of the probability times the difference squared, and then in the formula it doesn't have the squares, just like the book. See how it omitted the squares right there? So that was a mistake in this, in the text right here. Right? So that's something definitely to point out right there. Right? So what it does is it goes through and finds the sample variance for each point and plugs in 1, 1, right, for each thing, the sum of x squared, so it squares 1 and squares 1, that's how it gets 1 plus 1, plus the sum of x, which will be 1 plus 1 squared over n is 2, and then it does that for each sample point in the data set, which is described right here. So this is a long problem. This one takes a while. And notice it already has our x bar. Right? So what it wants you to do is find the sample standard deviation for every one of these points. And the nice thing is, once you get 3, 2, or once you do 2, 3, 3, 2 is going to have the same thing. Right? So you don't have to do the math every single time. Right? This, you know, once you figure out what 4, 5's sample standard deviation is, it'll be the same as what 5, 4 is. Right?
So the s squared
Is the variance.
is the variance.
Right. That's what it
It's
wants.
by the 1 plus 1 that you had just had it.
Right, because what it did was it found the variance of these 2 points for each thing. So it does the variance of every single point by plugging it into the formula, the shortcut formula that I just had written up. And really, this one do it too. Yeah. So let's go look at the formula. Let me write the formula down. So here's the sample variance formula. S squared equals. And the nice thing about 6.3, the thing we're doing today, it's not nearly as complicated as this section is right here. All right, it kind of puts together 6.1 and 6.2 into a nice thing called the central limit theorem. Right, which is a very nice, easy thing to use. It's pretty straightforward, really. So this section is really the tough part with this chapter. All right, so let's just write this down. This is the shortcut formula. Sum of x squared over n divided by n minus 1. So then in the view and example, that's how it comes up with. So what it does is it finds the sample variance of the first point, 1, 1. So the sum of x squared, so it squares each point and adds them together. And 1 squared is just 1. So that's why it's not included in there. Can we see that? So this one problem right here will take a while, right? It's pretty in-depth. And then they do it for the next point. So 1, 2. Notice here they do have the squared on the 2 because 2 squared is not 2, right? It's 4. And they just do it for every single point. Right? And this table is a little bit different than ours. Or no, maybe it's not. For some more samples are shown below, and then it actually goes through. It says, notice that for each sample of size 2, the sample variance is dependent on the difference between the 2 x values. That is to say, samples with an equal distance between the 2 x values will have the same variance. And they're saying equal distance from the mean, right? Thus, these samples of 2 can have 5 possible variances. S squared equals 0, S squared equals 0.5, S squared equals 2, S squared equals 4.5, and S squared equals 8 for a difference of 4. So that's actually how it works out. So we don't really have to go through and do every single one. See as it goes through this? But I still want to kind of show how they came up with this. It says, use the table displaying all 25 possible samples to find the probabilities of the other 4 possible sample variances. So that's all. For all of those samples, we only have 5 different variances for all those sample points. There's only 5 separate ones. So I'm going to go back to that list of all the sample points, and we'll just do a few variances and show that we're going to get one of these 5 values. All right? So let's go back and do that. So here's our data. Right. So we've already done 1, 1, and 1, 2 was done in the view and example, right? Right? So let's go through and let's do 1, 3. So for 1, 3, our sample variance is going to be S squared equals the sum of each piece squared. So it's actually 1 squared plus 3 squared, which the view and example isn't putting the squared on 1 because it's the same thing. Right? Does that make sense? And then minus the quantity 1 plus 3 squared divided by 2, because all of these sample points have 2, and then 2 minus 1. Right? They're all 2. So then go through and do the math on that. So we get 1 squared plus 3 squared is 10, right? Minus 1 plus 3 is 4 squared is 16 over 2. Right? This becomes 16 over 2. Does everybody agree with that? This piece is? 16 over 2 is just 8 over 1. So we get 10 minus 8, 2 over 1. So we get 2. There's the sample variance for those 2 points. And what you'll notice is the variance is actually the distance between the 2 values. That's what it's going to be for each time. So let's do 1, 5. Right, and see if we get the variance to be 4. So let's do 1, 5. We get S squared equals 1 squared plus 5 squared minus 1 plus 5 squared over 2. And then I'm just going to put divided by 1 because it's 2 minus 1. All right, so that's equal to 26 minus, this is equal to 36 over 2, right, this piece? Because 1 plus 5 is 6, 6 squared is 36 over 2. So 36 over 2 simplifies to what? 18. 2 goes into 36, 18 times. Divided by 1. Bless you. So we get 8 over 1, not 4, this one's 8. Sorry, I mistakenly said 8, or 4, because that's the distance between the 2. So we need to go through and do this process for each sample point. Now the nice thing is, since I've already done 1, 5, I've found the variance for 5, 1. It's going to be 8 as well, right, for each sample point. So as you go through, each set of sample points, I should say, because they're each 2.
So if we need to do that for every one, why is there only 4 or 5 places to put?
Well, because that's all the different variances we get.
Okay.
Yeah, from all of these. Because this one and this one's going to be the same, right? This one and this one's going to be the same. And the way it works out is there's actually only 5 variances that we get from all of these different sample points. Because as you go through and do it, so let's do 5, 5 and see what we get. So I'm going to erase it. Let's see what the variance of 5, 5 is. S squared equals, now on a test I would not make you find the variance for all of these sample points. I mean that would take you 25, 30 minutes for this one problem. Right? So I would give you that data. So it's the sum of x squared. So let's do it for 5, 5 and see what we get for the variance. So you get 5 squared plus 5 squared minus 5 plus 5 squared over 2 divided by 1. All right. So this equals 5 squared plus 5 squared is 50, right? 25 plus 25. So we get 50 minus, what's 10 squared? So this is 100 over 2, which is 50 over 1. So what's our answer here? 0. Anytime the two sample points are the same, there's no variance, right? They don't vary. So 1, 1, the variance is going to be 0. 2, 2, the variance is going to be 0. 3, 3, 4, 4, and 5, 5. The variance is going to be 0. So really there's only 5 variances because there's 1, 2, 3, 4, 5 sets right there. And then it repeats 1, 2, 3, 4, 5. And then it repeats 1, 2, 3, 4, 5. And then it repeats again. And then it repeats again. All right? So what we need to go in is find out for each one what the variance is. So for 1, 1 it was 0. For 1, 2 it was 0.5, right? And then we just did 1, 3. We got 2. We did 1, 5 and got 4. Right? So let me write those down. So 1, 1. 1, 2. 1, 3. 1, 4. 1, 5. So here was our sample point. And then our s squared, our variance here was 0. The variance here was 0.5. That was given to us in that view and example. What did we get for 1, 5? What was the variance? 8. Yeah, we just did it over there, right? 1, 5, the variance was 8. So let's do these other two. We haven't done them yet. Or did I have one? Yeah, I did do 1, 3. What was 1, 3? 2. And then let's just go ahead and do 1, 4. S squared equals 1 squared plus 4 squared minus 1 plus 4 squared over 2 divided by 1. So what's 1 squared plus 4 squared equal? 17. 1 plus 16 is 17. Minus 1 plus 4 is 5 squared. So that's 25 over 2. Which is what is a decimal? What times 2 going to 25? 12.5. Over 1. So we get what? What's 17 minus 12.5? 4.5. Isn't that each of the 5 variances we got total? Let me go back to the view and example. So see how it kind of starts to repeat? So for 1, 1, the variance was 0. 1, 2 is 0.5. 1, 3, the variance was 2. 1, 4, the variance is 4.5. 1, 5, it's 8. Then for 2, 1, notice 2, 1 and 1, 2 have the exact same variance, right? 0.5. And then 2, 2, the difference between the two values is 0. 2, 4, the variance is 2. It doesn't have 2, 3 on there, right? And it doesn't have 2, 5. Wasn't written in there. But it will be 4.5 and then 8 respectively, right? So you'd want to go through and do this again, right, and do it for each of the ones that we don't have. And then add together the probabilities. Okay? Now notice how the variance really depends on the distance between the 2 points. If the distance between the 2 points is 2, the variance is 2. If the distance between the 2 points is 3, the variance is 4.5. If the distance between the 2 points is 4, the variance is 8. Right? And I know that's not very, it's not symmetric in the sense that you would think it would keep increasing, right? You'd think the variance should be 3 here, but it's not. It's 4.5. So that's what it's going to be for each of the sample points. So really, I could go in and keep writing it, right? I could say 2, 1, which we already found, 2, 2, 2, 3, 2, 4, and then 2, 5. So the variance for 2, 1 is 0.5. The variance for 2, 2 is 0. Variance for 2, 4 is 2. And we'd have to go through and find the variance for the other two just to make sure we don't get the wrong one in the wrong place. One of them is going to be 4.5 and the other one is going to be 8. Do I have a board under that? So there's my 1, 1 samples. Or they might not actually. Let's try it. So let's find the variance for 2, 3 and 2, 5. This problem is definitely the most difficult in the entire chapter, this one problem right here. There's a lot to it. All right? There's a lot to do. So let's find the variance for 2, 3 and then the variance for 2, 5. So s squared equals 2 squared plus 3 squared minus 2 plus 3 squared over 2 divided by 1. So 2 squared plus 3 squared, 4 plus 9 is 13, right? 13 minus 5 squared is 25 over 2. So then 2 plus 3, 5. What do we get? 12.5 over 1. What do we get right here? 0.5. So that's good. That's one of our 5 values that we need to get. And you notice the difference between the two numbers is 1. Both times the distance between them is 1. The variance is 0.5. All right? Then let's finally do that last one. 2, 5. S squared equals 2 squared plus 5 squared minus 2 plus 5 squared over 2 divided by 1. All right, then we go through. What's 2 squared plus 5 squared going to be? 29. 4 plus 25. 29 minus 5 plus 2 is 7. 7 squared is what? Anybody know? 49. 49 over 2. Which reduces to what? 24.5 over 1. So what's our answer here? 4.5? So now we can use this pattern of the values being the same. The variance is 0. When the difference is 1, the variance is 0.5. When the difference is 2, the variance is 2. When the difference is 3, the variance is 4.5. And then for this section, there's no difference of 4, right, for that piece. So that's what this little box right here is talking about. Let me snip that out so we can really read it. Okay, it says, notice that for each sample size 2, the sample variance is dependent on the difference between the two x values. That is to say, samples with an equal distance between the two x values will have the same variance. Right? So 2, 5 or 2, 4 would have the same variance as 1, 3, right? Didn't 1, 3 have a variance of 2 from the chart we just did? Because it has a distance of 2. Look, 1, 3 has a variance of 2. So if it's the same number, the variance is 0. If it's 1 different, the variance is 0.5. If it's 2 different, the variance is 2. 3 difference, 4.5. 4 difference, the variance is 8. All right? So now I could go back to that chart and put the variance for each of the data points. And then I just have to add together the probabilities. Right? So let's remember this as we fill out our chart. Okay. So let's put our 5 variance. So that's where the 5 numbers come from. Does that make sense now, Crystal, how they only have 5 places for it? So our variances are going to be 0, 0.5, 2, 4.5, and 8. Now, 0, for it to have a variance of 0, that means the numbers are the same. So I need to add together all the probabilities where my sample points are equal. So I need to add this one, plus this one, plus this one, plus 4, 4, plus this one, 5, 5, plus that one. So it's 0.16 plus, so 0.17, 0.21, 0.22, 0.26 would be the probability right there. So what that means is my chances of picking a sample point that has a variance of 0 is 26%, right, or 0.26. So now let's do it for 0.5. What's the difference between the points to get a variance of 0.5? 1. So that'll be this point. So we had 0.4 plus 0.4, and now we have 2, 3 that we have to add. So 0.8, 0.1, then 3, 2 we have to add together, 0.12, and then 3, 4 we have to add together, 0.14, then we have to add 4, 3, 0.16, and 4, 5, 0.18, and then finally right here, 0.18 plus 0.02 is 0.2. And then keep going from there. I know this problem, there's a lot going on right here. And then keep going. So the difference, if the variance is 2, that means they have a difference of 2. So let's add together all those sample points. And the nice thing with this might be to actually print this thing off and kind of strike it out as you count the probability. You see what I'm saying? And actually put a slash through it so you don't double count something. So 1, 3, 0.08. Because I'm doing this kind of fast, I might actually miss something. 0.08, and then we need a difference of 2. So right here, 0.01. So that's 0.09. And then what other ones have a difference of 2? Right there, 3, 5. 0.09 plus 0.04 is 0.13. 0.14. Right there, 0.18. There it is. So this would be 0.18. Notice how my probabilities are going down each time. So for 0.5, if it has a variance of 0.45, the difference between the sample points is 3. So let's go there. So 0.04 plus 0.02 is 0.06. Those don't have a difference of 3. This 0.06, so that's 0.1. And then right there, 0.12. And the last one I don't even have to count, right? I could add all those together and subtract from 1, but let's verify it. So how much probability have I accounted for? So let's add those 4 probabilities together. I use my calculator so I don't make a mistake. Plus 0.2, bless you. Plus 0.18, plus 0.12. 0.76. So then minus 1. So I need to get 0.24. So I'm going to count all the sample points. I think I missed something somewhere. With a difference of 4 would only be this one, right? And this one. So I've missed something somewhere going through. I did it a little too fast. You guys see which one I missed?
I think you missed that 3, 1.
So the difference of 2?
Yeah.
Okay. This one right here?
Yeah.
Okay. Which that would make sense because I'm coming up with 0.118. Right, I need 0.24, and I'm coming up with 0.16 when I add together this one and this one. Yeah, so that makes sense. Right? 5.1 and 1.5, the probability will be 0.16. So I missed one right here, huh? I missed this one. So that should be 0.26 as well? Okay. Whoa, not 0.26. Now, on a test, I would not make you go through that systematic effort like that. I mean, look, that took me 25 minutes to do it in class right here. Something I might give you, though, is this chart, and then ask you what this question asks you. Is it a biased or unbiased estimator? All right, so let's keep going on this problem. All right, good. And see, I counted the probabilities, and I know they have to be equal to 1. So that's why I knew something was wrong, right? I'm kind of checking myself as I'm going through it. Find the population variance, sigma squared. All right. So how do we do that? Now here, this is where they mix formulas. So there's the chart we came up with, basically. Our numbers are a little bit different, right? Then what it asks is to find the population variance. So it's the probability of x times x minus mu squared. Now, look in here. So they do it for each data point. But where do they come up with this 2.9 for mu? How do they come up with that?
How did they come up with mu?
Yeah, how do they come up with mu?
0.26 times 0 plus 0.2 times.
Right. No, not for the variance, though. We'd want it for this right here, for the actual population. Yeah, they find the expected value right here, right? So let's do that expected value and make sure we come up with... Now, we're not going to get 2.9 because our problem's going to be a little bit different. But mu is the expected value of the population, right, which is going to be the top one. So it's going to be 1 times 0.4 plus 2 times 0.1 plus 3 times 0.2 plus 4 times 0.1 plus 5 times 0.2.
2.6.
Ours is 2.6, right. So I'm going to go, let me erase this one. So the expected value of x is equal to mu, or expected value, I don't need to put the summation, which is equal to the sum of x times the probability of x. And we found that mu was equal to 2.6. So then our variance, right, sigma squared, is going to be equal to the sum of the squared differences times the probability. Notice this is x, not x bar, right? This is the population, not the sample. So this is equal to, my first point is 1, so it's 1 minus 2.6 squared times its probability, which is 0.4. And in the book, it writes the probability first. It doesn't matter. Right? 3 times 2 is the same thing as 2 times 3. And then plus, let's keep going. 2 minus 2.6 squared times the probability of getting a 2, which is 0.1, plus 3 minus 2.6 squared times the probability of getting a 3, which is 0.2, plus 4 minus 2.6 squared times the probability of getting a 4, which is 0.1, plus 5 minus 2.6 squared times the probability of getting a 5, which is 0.2. so let's put that in the calculator. Is that bright enough? That's not very bright, huh? Open. That's a little better. All right, so we go. Open parenthesis, 1 minus 2.6 squared times 0.1 plus, open parenthesis, 2 minus, and I can even go second answer. Everybody see that? Because answer, I can either retype 2.6 or put answer because it's going to pull whatever that result is. So 2 minus 2.6 squared times the probability of 2 was 0.1. And I have it all written out over there, right? Plus 3 minus 2.6 squared times 0.2 plus, open parenthesis, 4 minus 2.6 quantity squared times the probability of achieving a 4 was 1.1 plus, open parenthesis, 5 minus 2.6 squared times the probability of getting 5 was 0.2. And hidden. So that's my sample, or my population variance, not my sample variance. So this equals 1.672. Let's go back to the computer. It says type an integer or a decimal rounded to 2 decimal places. So what is it? 1.67. What have I done wrong here?
I got 2.44.
Yeah, I might have made an error in my calculator. Let me look at it. Maybe putting that answer wasn't the best thing to put there. So let me go back and add in. I do have the squares. What'd you get, Morgan? Let's put that one.
2.44.
Okay, let's see if that's right. So I missed something on my calculator. I entered something in wrong. Because you did this formula, right? That's the thing you put in? Yeah, I must have put something in wrong somewhere. So that's not right. Anybody else call it that 1.672? No? Okay, so it's just my error. That's good. Okay. And once, when you guys go in and do this, the numbers are going to change. Okay. Determine if S squared is an unbiased estimator of the variance. So is our sample variance an unbiased estimator of the population variance? They need to be equal to be unbiased. So it's either going to be biased because they're not equal, or it's going to be unbiased because they are equal. And then notice for A and B, they mix it. They say the statistic is biased, which is equal, so that obviously can't be the case. And then it says it's unbiased because they're not equal, so I know it's not going to be either A or B. That doesn't make any sense. It's unbiased if they're equal, it's biased if they're not equal. So we need to find the expected value of S squared, which is easy. You just multiply S squared times its probability, right, for each point. So let's find our expected value of S squared. Let me make sure I do this right this time in my calculator. Okay, so let's do it. So it was 0, which you don't even really need to worry about 0, times 0.26 plus 0.5 times 0.2 plus 2 times 0.26 plus 4.5 times 0.12 plus 8 times 0.16. And we get the exact same value. Right, you guys get 2.44 when you did that? So I don't know what I did in my calculator to mess that one up. I need to go redo it. So what's our answer here? D. It's unbiased because the expected value of our sample variance is equal to 2.44, which is equal to the population variance. All right, so there's our answer. Okay? This is a very in-depth problem. There's a lot of tedious steps. And you notice right here I made a mistake somewhere. Right, just going through and doing this, I made a mistake. I think I might have put a plus somewhere instead of a minus, is where I messed up. Okay? And there's still a couple parts. Find the sampling distribution of the sample standard deviation. So all we do there is just square root each of the variances. What's 0 square rooted? 0. What's the square root of 0.5? You guys have a guess? What does it say to round to? 3. 0.707. Is that what you guys got when you square rooted 0.5? How come it's going up? Usually when you square root it, the number gets bigger, right? What's going on there? It's because when you square root a number between 0 and 1, it actually gets smaller. Because it's like you're taking 1/2 times 1/2. So you're taking 1/2 of 1/2, which is 1/4. So anytime you square a number between 0 and 1, it gets smaller. What's the square root of 2? No, 2 squared is 4. What's the square root of 2? Right. Right. And then you got to do, mine doesn't give me the second square root of 2. Then I need to do fraction to decimal. Oh, you know what? Do the trick right there, 2.0, and hit enter. If it just returns square root of 2, put 2.0. You get 1.414. It's no coincidence that this number is double that number. That's the way this is working out. Right? Because remember, the variance is squared units. What's the square root of 4.5? 2.121. And then finally the last one, square root of 8. I'm going to put square root of 8.0. 2.828. And the probabilities are going to be the same. Because if it has a variance of 8, the probability is going to be, the probability of a standard deviation of 2.828 is going to be the same value. Okay? And if you go through the view and example, you'll notice that. See how the probabilities are the same? So that'll be the same for our problem. Right? So this one's going to be 0.26, 0.2, 0.26, 0.12, 0.16. All right. Determine if S is an unbiased. So is our sample standard deviation an unbiased estimator of the population standard deviation? What is the population standard deviation?
Population variance, square root.
Right, the square root of the population variance, square root of 2.44. What is the square root of 2.44? 1.562. So I'm just going to write that down right here so I have it. So my population variance is 1.562. Or standard deviation, my population standard deviation, excuse me. So let's find our sample standard deviation by just doing the expected value. This times this plus times that, just like we've done. let's go in and do that. So clear 0 times 0.26. Once again, you don't really have to do that one. 0.707 times 0.2 plus 1.141 times 0.26 plus 2.121 times 0.12 plus 2.828 times 0.16. What do we get for S? What'd somebody get? Make sure I did it right. Round to 3 decimal places.
1.216.
1.216?
I got 1.145.
That's what I got. 1.145. So there might have been you might have missed just a decimal or something in there. Times 0.2. I'll see. 0.2, 0.26, 0.12, and 0.16. Huh. That's weird. If you look through it, there's probably a small glitch, which if you want to leave that up, Jessica, and then I'll look at it. So are those equal? Either way, even if you would have got that number, it still wouldn't be the same, right? They wouldn't be equal. So what's our answer right here? Is it biased?
Yeah.
Yes. If they're not equal, it's biased. So there's two things that say biased. There's A and C, both say S is biased. The reasoning, though, is different. One says it's biased because they're not equal. One says it's biased because they are equal. So which one is it? It's got to be not equal, right? A. And then right here's the check of if we did ours right. What's going on? Let me do it one more time. So I'm not even going to worry about 0. So 0.707 times 0.2 plus 1.4. 1.414 times 0.26 plus 2.121 times 0.12 plus 2.828 times 0.16. There, now I got the one that Jessica came up with. Which was 1.216. That's why with this stuff I'm concerned with the work just as much as the answer. And there we go. So that is the right answer. Did you come up with that time, Mark? If you did it again, did you come up with that number? Okay. I'd have to go look at the calculator where I messed up. I'm just trying to go a little too fast. Okay. So it took us 45 minutes to do this problem. All right? This thing is long. That's why there's only 5 questions on this homework assignment, because they're all pretty tedious and long. All right? As long as you go by your step-by-step method, that's why I really encourage you guys to show all your work. So that if you do make a dumb mistake like I've done, all right, you don't get killed for it. All right? I really want to know that your thinking is correct. This is way more important than this down here, which I know runs counterintuitive to how you grew up, in high school, growing up. Right? They just care about this. They don't really care about this part. Or college, it's the other way around, right? The process is much more important than the destination. Okay? There it is. So now when you go back and do this problem, the numbers will be a little different, but at least we went through it. And you understand why. Okay? All right, so let's start on the next section. And these will be a lot simpler because the samples are a lot smaller, right? Okay. why that pop-up thing's showing up now. Let's go chapter 6, textbook 6.3. This section is much more straightforward than 6.2. Right? There's a lot less roundabout to it. It actually gives you some pretty easy formulas to use. And this will be the last section that'll be on the test. Now, on the test, I would give you the probability distributions. All right, I wouldn't make you construct them, but I might ask you, is it a biased or unbiased estimator? So you'll have to go through and find the expected values of each, but I'll give you the variances. Right? So, no, I might not give you the variance, but I will give you the chart like that. Like the first question on that homework assignment, how we had to fill that chart out, I'd give you that chart. Okay, I wouldn't make you construct that chart. Because that's really what took most of the time. All right? So you'll notice this section is really about, or this chapter is the expected value. You have to know how to find the expected value. Right? So let's get in here. Okay. Estimating the mean useful life of automobiles, the mean number of crimes per month in a large city, the mean yield per acre of a soybean farm, are practical problems with something in common. In each case, we are interested in making an inference about the mean of some population. So we don't want to go out and pick every soybean in the farm and find the weight. You know, we'd like to find a sample of a small area and use that to tell what our yield's going to be for the entire farm. All right, we'd go out and take a half-acre sample of a 5,000-acre farm. Right? As we mentioned in Chapter 2, the sample mean x bar is in general a good estimator of mu. We now develop pertinent information about the sampling distribution for this useful statistic. We will show that x bar is the minimum variance unbiased estimator in view of mu, which I know I didn't define that word, but it's showing that x bar is a good estimator of mu. All right? Our sample mean is a good estimator of the population mean. Now let's think back to that thickness problem. Remember the metal thickness? Where they did 1,000 samples of 11 steel sheets and took the average thickness of each of those 1,000 samples? Remember that problem we talked about a couple days ago? On the next page, it creates a probability distribution of all those samples. So whatever the average was for the sample, it puts it in a histogram, like in a class. All right, and it creates a histogram of all the averages for those 1,000 samples. And it's listed right here. Now the average of the uniform distribution was 175 exactly. The average of our sample distribution, the mean of our sample distribution is 175.2, which is very close to 175. So this is the frequency of the averages of each of my samples. So if I took a sample of 11 sheets of metal, there was one sample that had an average width or an average depth of 164 millimeters. But it only happened once. See that? Or maybe that's twice, because 5 would be about right here. But look which ones show up the most. The ones right here in this 172 to 176 range. Now there are some, like this 169, or about 69, this would be 170. So there were approximately 50 samples that had an average of 170 millimeters. But look which one ends up showing up the most. It's right here in this region, which this is approximately normal. See how our sample mean is approximately normally distributed? Look back. Note that the simulated value, mu of x bar, is very close to mu. So the sample mean and the population mean are very close. That is, the simulated sampling distribution of x bar appears to provide an unbiased estimate of mu. They're not exactly the same, but they are very close, especially on a relative sense. When you're talking about 175 millimeters, 0.2 millimeters is very small compared to 175. So the difference between the two is what we would call negligible. It doesn't really matter. The true sampling distribution of X bar has the properties given in the next box. Assuming that a random sample, that's very important, the sample has to be chosen at random. Right? I can't go in and pick the metal sheets that look the thickest for each of my samples. That's not a random sample. Of n observations, so our observations here were 1,000. We had 1,000 observations. Right? Or no, 11 is the size of the sample, excuse me. So it says, assuming only a random sample of 11 observations in that case has been selected from any population. This is what we've been building up to in this chapter. All right here. Properties of a sampling distribution X bar. So everybody write these down. The mean of the sampling distribution of X bar equals the mean of the sample population. That is, mu of X bar equals the expected value of X bar, which is equal to mu, which is also the expected value of X. So the sample mean equals the population mean. It's very important. That means it's unbiased. The standard deviation of the sampling distribution of X bar equals, so our sample standard deviation is equal to our population standard deviation divided by the square root of the sample size. Where in that case the sample size would have been 11. And that's just the formula, all right? So you don't really need to be concerned with why that is. You just need to know that that's the formula. So step 1 says, my mean of my X bar is equal to my population mean, which I just kicked out the expected value of X bar because that's what the mean is. And 2, my standard deviation of my sample is equal to my population standard deviation divided by the square root of the size of the sample. That's it. That's all we're going to use for this section, is these two simple formulas. The means are equal. The sample standard deviation is just the population standard deviation divided by the square root of n. You'll be given these two values in your homework. You'll just have to plug them into the formula. All right? So let's go back and look at that uniform distribution again. So those are properties of the sampling distribution X bar. Now let's think about, what was our formula for the mean of a uniform distribution? You guys remember?
Formula for the mean?
The mean of the uniform, do you remember? C plus D over 2. That was just the average of the two endpoints. So you take this number plus that number divided by 2. So it was 175, right? Was the mean of our population. What was the formula for the standard deviation? You guys remember? Let's do an example. It had that square root of 12 thing in it. So my mean for a uniform is C plus D over 2, which in this case would be 150 plus 200 over 2, which is 175. So my mean is 175. My standard deviation was equal to, do you guys remember? D minus C over the square root of 12. So in this case, it would be 200 minus 150 over the square root of 12, which is 50 over root 12. So sigma equals what to 3 decimal places? 50 divided by second square root of 12. And I'm going to do 12.0 so I get a decimal. 14.434. So this is my population mean and my population standard deviation. So according to my properties of a sampling distribution, my sample mean is going to be equal to my population mean, which is 175. My sample standard deviation is going to be equal to my population standard deviation divided by the square root of n. So that's going to be equal to 14.434 divided by the square root of how many pieces were in each sample? 11. So do 14.434 divided by second square root of 11. Excuse me. So what this shows is our sample has much less spread than our population does. Our population has a lot of spread because our population is uniformly distributed. Right? You guys see that? So there's just as much area under the curve at the endpoints as there is right in the middle. That's not the same with our sampling distribution. Right? Our sampling distribution, most of the area under the curve is right around the mean. So that's why this standard deviation is much smaller than the uniform distribution. Right? Than the population distribution. Okay? And that's all really we have to do for these homework assignments, is plug them into these formulas. Right? And then 4.35, which I did it out to 3 decimal places. 4.352, same thing. Thus, the approximation we obtained at 6.6, the sample standard deviation is 4.38, is very close to the exact value of 4.35. The 4.38 comes from this mini-tab printout. See what it has for the standard deviation, 4.38? Right? It can be shown, proof omitted. That's 2 very nice words in mathematics, so you don't actually have to go through the proof. That the value of the variance is the smallest variance among all unbiased estimators of mu. Thus, x bar is a good estimator for mu. All right? 2 theorems provide this information. What about the shape of the sampling distribution? And that the 2 theorems are on this page. So this is just of the sampling distribution of x bar. Right? The other applicable when the sample size n is large represents one of the most important theoretical results in statistics, the central limit theorem. So first let's write down 6.1. Theorem 6.1. Theorem in math just basically means definition. It's something that always works. All right? It's concrete. If a random sample of n observations is selected from a population with a normal distribution, the sampling distribution of x bar will be a normal distribution. Now that's not very hard to believe. If the population is normally distributed, if I take a sample from it, the sample is going to be normally distributed. So there's not really a whole lot to that theorem. So theorem 6.1 says if the population is normal, the sample is going to be normal. Which doesn't really tell us a whole lot. You know, big deal, of course. That makes sense. If the population is normal, the sample will be normal. 6.2 is really where the magic is. Right? The central limit theorem is very, very nice. I mean, it says right here, it's one of the most important theoretical results in statistics. Theorem 6.2, you can call it the CLT, the central limit theorem. And look at the first sentence right here. Consider a random sample of n observations, so it's exactly the same start as 6.1. Selected from a population, any population. 6.1 says the population has to be a normal population. 6.2 says it doesn't have to be normal. It can come from any population. It could be uniform. It could be skewed. All right, it could be skewed left, skewed right. Uniform, it could be bimodal. It could have two peaks. Right? It doesn't have to be either of them or any of them. But it's still, no matter what the shape of the population is, X bar will still be normal. That's really pretty amazing. All right? Then, when n is sufficiently large, and we'll answer this question of what constitutes sufficiently large later on. Okay? The sampling distribution of X bar will be approximately a normal distribution with the means being equal and our sample standard deviation being the regular standard, the population standard deviation divided by the square root of n. The larger the sample size, the better will be the normal approximation to the sampling distribution of X bar. The bigger the n, the better approximation you get. So what that's saying is you need more observations before you have a better idea. And really the number that we settle on with n is 30. Really you want about 30 observations before you can really conclude that it's a good approximation. But as of right now, we are not attaching a value to what makes n sufficiently large. We're just going to say it. And it really depends on the situation. Right? If we're talking about the population of the Earth, 10 people is not sufficiently large enough. All right? If we're talking about the population of all the people in the College of Education right now, 10 people might be sufficiently large enough. Right? So it really depends on the size of the population tells us how n is, if n is sufficiently large or not. So 6.1 says if the population is normal, the sample will be normal. 6.2 says the population doesn't even have to be normal and the sample will still be normal. Which is really pretty amazing. All right? So let me see which example. Yeah, this next really shows some cool pictures that really talks about 6.2. And these two theorems are on page 285. So that's a good thing to do in your notes when you write the theorems down. Put the page number there on. Page 285. I'll give you another minute to write those down.
Can you move that over? That board over there? So I can finish writing that.
This one? Oh, move this way? So this was example 1 from this section, right?
Yeah, it was on page, it was...
Example 6.6. 6.6, right?
Oh, the table was...
Yeah, right. So this is a specific example of this general topic right here. This one is much more straightforward than 6.2 was. We're already showing this theorem states that X bar will be an unbiased estimator. All right, that's what it's talking about here. If n is sufficiently large. If n isn't sufficiently large, we don't know. There's no conclusions we can draw. So let's look at some pictures right here. So look, my original population could be any one of these 3 distributions. Does everybody agree that these 3 are definitely not normal? They're symmetric. The first 2 are symmetric, but they're definitely not normal. Bless you. This one is skewed to the right. This one's kind of like an exponential decay curve. Right, that's kind of what that one looks like. The first one is a uniform. This one is what I call bimodal. It has two modes. It has two values that show up the most. But look what happens is I make n big. So if I take sample size of 2, and then I take a sample size of 5, and then I push my sample size all the way out to 30, look at what the shape of the distribution is. It creates a normal distribution. When my n was 2, this isn't quite normal. When my n is 5, it's starting to look normal. When my n is 30, it's definitely normal. All right? Which means I just randomly select 30 observations from the population. That's what the central limit theorem means. No matter what the shape of the population, if my sample size is big enough, my sampling distribution will be approximately normal. And then the bottom one is trivial. I mean, of course, the bottom one is theorem 6.1. If the population's normal, notice it doesn't even matter what size my sample is. All three of the sampling distributions are normal. Moreover, because of the central limit theorem, the sum of a random sample of n observations, sum of x, will possess a sampling distribution that is approximately normal for large samples. This distribution will have a mean equal to n times mu and a variance equal to n times sigma squared. Proof of the central limit theorem is beyond the scope of this book, but it can be found in many mathematical statistics texts. If you want to know this proof of the central limit theorem, we have a class called Stat 403 where they cover that. All right? No, you guys aren't too interested in that? All right. So you just have to take it like it's the word, right? Like it's gospel. That's the way it works. Okay. Which one did I want to do? Yeah, let's do this next one. All right, so 6.7. Let's do example 6.7. Using the central limit theorem to find a probability. Suppose we have selected, and then let me read this first thing up here. Sample size must be before the normal distribution is an adequate approximation to the sampling distribution of x bar. For most sample populations, sample sizes of n greater than or equal to 30 will suffice for the normal approximation to be reasonable. All right, if you really want a good idea of what the average is, you need to do it 30 times. Another way to think about that is if you have a baseball player, you wouldn't want to say his batting average after 4 at-bats. That's not indicative of what it's going to be in the long run. But basically, after 30 at-bats, you have enough data to know what it'll be in the long run. So no matter what you're doing, if you do the experiment 30 times, you'll have a good idea of what your average is, of what it will be. So if you say, how long does it take to clean the kitchen? Well, you need to clean the kitchen 30 times and find out your average from each of those, and that'll give you a good idea of how much time it takes. Because one time it might take you 30 minutes, one time it might take you an hour, then 45 minutes, then 50 minutes. You'd want to do it 30 times before you have a good approximation. And that's true with anything. That's a pretty interesting number, that 30. Right? Suppose we have selected a random sample of n equals 36 observations. That's definitely sufficiently large. From a population with a mean equal to 80 and a standard deviation equal to 6. So right there, they're giving us the mean and the standard deviation, which is what they're going to do on your homework. Right. It is known that the population is not extremely skewed. Sketch the relative frequency distributions for the population and for the sampling distribution of the sample mean, x bar. So let's sketch it with a mean equal to 80 and a standard deviation equal to 6. It says it's not extremely skewed, all right? So it doesn't say it's normal. It just says it doesn't look like this. Right? That's extremely skewed. All right? So you can create a shape that looks pretty much like it's normal. All right. So let's say that's the distribution. What did it say the mean was? 80. So what number will be one standard deviation above the mean? 86. What number will be one standard deviation below the mean? 74. And then what? 68. And then 62. And then it'll go up to 92. And then 98. All right. So now let's do it for X bar. So we know the means are going to be equal, right? What's not going to be equal is the standard deviations. So that's our population, right? So I'm going to call this mu, and then I'm going to call this distance sigma. Now let's do it for the sample. Is our mean going to be the same? What did the central limit theorem say?
Yes.
Yes, they will be equal. And this red marker has just expired. So I'm going to redraw it. So the sample mean is going to be the same, which I'm going to call 80, and it's X bar. But what's my sample standard deviation going to equal? What's the formula for it from the central limit theorem?
Deviation divided by the square root of n.
Sigma divided by the square root of n. What was sigma?
6.
6 over what was n?
36.
36, which equals 6 over 6, which equals 1. So my sample standard deviation is only 1. So this distance is sigma of X bar. And then we have 82, 83. So 83 is 3 standard deviations above the sample mean. 78 and 77. So 77 is 3 standard deviations below the sample mean. And here's a couple sketches that the book comes up with. So its population, notice it's not skewed, but it didn't make it normal. See how it kind of put some waves in it on one side? That one's not normal, but it's not extremely skewed either. Now I could come up with an infinite amount of these right here. Because I could draw this line, and I could have went up here, and then maybe down, and then maybe back up. Right? Because there's no stipulation on what the population is. There is a stipulation on the sample mean, though. But notice how my numbers down here at the bottom are the same, right? 80, 86, 92, 98, 80, 74, 68. And then there's our sampling distribution of X bar. Oh, and I need to put this as mu of X bar, not just X bar. There we go. This one has to be normal. This one doesn't. Okay? Everybody good so far? Kind of understand what's going on here? This thing I could have made any shape at all. I could redraw this line and put a hump there, and then a hump there, and then have it come down, and then maybe another hump there. Right? It's not extremely skewed, but we don't know exactly what it is. Notice what your book says right here is, one possibility is shown in figure 6.11a. That's not the only possibility. And then what does part B say? Part B says, find the probability that X bar will be larger than 82. So what area under the curve is that? So I want to know what the area is over here, right? Because it says larger than 82. Since this is normal, I can convert this into my z-chart, right? Determine what my area is from my z-chart. And the z formula is exactly the same. Look at z. Your normal random variable, in this case 82, minus 80 divided by 1. X bar minus mu of x bar. Yeah, this whole thing is x bar instead of x. So, in terms of x, this is the number. In terms of z, it would be 0, 1, 2, 3, negative 1, negative 2, and negative 3. And the reason I know that is because 82 minus 80 is 2 divided by 1. All right, does everybody see that? So now what I need to do is find out the probability. So what's the probability of z being greater than 2? That's an equivalent statement to saying the probability that x bar is greater than 82. And remember, the or equal to does not matter. So let's go look at our z-chart. And it's on 773, right? So what do I have to do to find that tail?
Look for the z-score of 2 and then subtract that from 0.5.
From 0.5, right? Because I'm looking for the area that's out here, right? So I need to do 0.5 minus whatever it is at 2. So 0.5 minus 0.4772. Which equals point what?
0.223.
So your chances of the sample mean, your observation of your sample mean exceeding 82 is only 2.3%. That's it. Not a very good chance. All right. And then there it is. Therefore, for x bar equals 82, z is x bar minus my mean divided by my standard deviation, which means z is 2. Then I go look at my table in Appendix A. The probability that x bar is greater than 82 is equivalent to the probability that z is greater than 2, which is equal to 0.5 minus 0.4772. And there's the probability. The key to finding the probability in Part B is to recognize that the distribution of x bar is normal with mean mu and standard deviation, population standard deviation over the square root of n. Okay? So what I want to do, rather than do another example from the book, let's go look at your homework. So that's the last section before the test. It'll be due Monday. Right? 6-3. So I'm pretty confident you guys will, understand well all these sections. 6-2 is the one that takes a little bit extra, right? 6-2 is the most difficult one from this chapter. Right? And it's due tonight by midnight. So let's go in and look at 6-3. Then we'll review on Monday, and then the test will be Tuesday at 9 a.m. So that's why I have the quiz, the exam 3 review, chapter 5 and 6, due 7/7 at 9 a.m. All right, go. Bless you. Right. So first it asks you a question, just like most of the homework assignments. Basically, this is just regurgitating the definition, right, from the section. So I'll let you guys look at that. This one's kind of long because none of these are very in-depth. They're all pretty straightforward. You basically find your sample standard deviation and construct your z-chart. Right, and that's it. Let's go look at number 4. Oh, great. They might have signed me out of here. Which happens sometimes if you let it sit there too long. me refresh and see if this page pulls back up. Isn't technology great? Yeah, I think it sat idle for too long and it kicked me out. So we'll look at one example, take about 10 minutes, and I'll cut you guys loose. There's no office hours today. All right, I have a meeting I have to go to at 11, so no office hours for me today. But there will be office hours on Monday for the review. So let's look at this one. Preview, go. What the heck? Why would it let me go to number 1? See, 1, okay. I was just looking at this in my office. Now this one's pretty straightforward. All you do, the mean is just the mean. The sample standard deviation will be 2 divided by the square root of n, which is 5. Right, because n is 25, so it'll be 2/5, so the answer there would be 0.4. That's it. I mean, they're pretty straightforward there. So to answer that, you just do the central limit theorem. All right? Let's do an example. What the heck? Well, let's do number 35 from the book then. I wonder what the issue is. Might have to get on Pearson and give him a piece of my mind. Wow. I don't know what's going on. Let me get number 30. If you guys go work on this homework and you encounter the same problem, let me know. All right? Shoot me an email, and I'll move the due dates around until we get it fixed. So I'm going to flip back to the document camera. So let's do number 30. And the answers are already given there to us, so... Oh, you can't really see them, though, because of the light, which is good. Okay, so let's do number 30. A random sample of n equals 64 observations is drawn from a population with mean equal to 20 and standard deviation equal to 16. This is the exact same problem you have on your MyMathLab. Just the numbers will change. So let's do number 30. So it says my n is 64. You'll notice most of your n values for these will be perfect squares, so that when you square root it, you get an integer. All right, it's not 65, it's 64. What's the square root of 64? 8. Right, so most of your n's will be a nice perfect square. Mu is 20, and it says my standard deviation is what? 16. So part A says, give the mean and standard deviation of the sampling distribution of X bar. That has a bar on it, even though you can't see it. So part A, so what's my mean of my sampling distribution going to be? Same mean, right. My standard deviation of my sample is going to be equal to my population standard deviation divided by the square root of n. So this is going to be equal to 16 divided by the square root of 64, which is 16 over 4, which is, no, not 4, 2. So there's the answer to 8. My sample mean is 20. My sample standard deviation is 2. Describe the shape of the sampling distribution. What will it be? Approximately normal, because n is sufficiently large. Any n greater than or equal to 30 is sufficiently large. So let's calculate the standard normal z-score corresponding to a value of x bar equals 16. Now, really, well, you're welcome to draw a picture on this, but I think we've kind of got enough of an idea. You don't have to, but you still can. I mean, isn't this distribution going to be 20 in the middle, and the standard deviation is 2, so it's going to be 22, then 24, and below is going to be 18, and then 16, right? So first I have to find this, or this doesn't say anything about probability, it just wants me to find the z-score that associates with 16. So let's just plug it into the formula. So z is equal to x bar minus mu of x bar over sigma of x bar. Or sub, I should say sub x bar. So this equals 16 minus 20 over 2 is negative 4 over 2 is. So my z value is negative 2, which makes sense. It's 2 standard deviations below the mean. And I can also do it for part D, which I'm not going to. But what do you think z will be when x bar is 23? Where's 23 appear? It's right here. 1.5, exactly. It's 1.5 standard deviations above the mean. Right? So let's z equals 23 minus 20 over 2, 3 over 2, which is 1.5. And notice E, F, and G basically account for the entire normal curve. So E says, find the probability that x bar is less than 16. I found the z value that corresponds to 16 is negative 2. So the probability that x bar is less than 16 is equal to the probability that z is less than negative 2. So this is E. F says the probability, put that the wrong way, the probability that x bar is greater than 23 is equivalent to the probability that z is greater than 1.5. And then G says the probability that 16 is less than x is less than 23 is equal to the probability that negative 2 is less than z is less than 1.5. So this one's going to be the tail, right? Because isn't it going to be, here's the normal curve, and then here's negative 2, so it's this stuff down here. You guys agree with that? Less than negative 2? And then this one says greater than 23, so here's the normal curve. There's 1.5, so it's all the values out here. And then for this one, it's going to be between negative 2 and 1.5, and it's all the area in the middle. So notice when I add all three of these together, I should get 1. Does that make sense? Because one's the left tail, one's the right tail, and then one's the middle. So let's go do them. So for both of these, I'm going to be doing 0.5 minus, right, for the tails, right? 0.5 minus something. And this one I'm going to be doing 0.5 minus something. This one I'm going to be adding two probabilities together, right? I'm going to be adding my z-score of 2 plus my z-score of 1.5. So let's go look at the table. Let me pull the table up. 773. There it is. Back that out a little bit. A little too white there. If this is going to work. Yeah. Let's go pull up the book. So my probability that z will be less than -2 is equal to 0.5 minus the probability that z is equal to 2, which is 0.4772, which we already found earlier. 0.0228. What about the probability that z is greater than 1.5? So that's the right-hand tail. So it's going to be 0.5 minus this value, right? 0.4332. What do we get there?
0.0668.
0.0668.
2.
What's that? So then what's this one going to be? It's going to be this number plus this number, right? 0.4772 plus, because that's the area between 0 and -2, plus the area between 0 and 1.5, which is 0.4332. We get 0.9. Okay. 0.9104. So this section definitely isn't too bad. It's kind of a review of chapter 5. All right. 6.2 is the difficult one. 6.2 is probably the hardest section we've covered up to this point in the entire class. Okay. But that's it. So that's the spiel. So you have an assignment due tonight. 6.2 is due tonight. If you have questions, shoot me emails. I'll try and check them. Today's going to be kind of crazy for me. I got a lot of stuff to do. But I'm going to intermittently try and look at them at least. Okay? So 6.2 is due tonight. 6.3 will be due Monday. We'll review Monday for the test and then take the test Tuesday. The review for the test is right here in the same spot. Exam 3 review. There it is. Know all this stuff, right? So know about uniform, know how to calculate a z-score, know the definition of parameter statistic sampling distribution, know the definition of point estimator, unbiased, biased, be able to find the sampling distribution of a sample statistic, and then section 6.3. So this test only has 6 sections on it, right? 3 from chapter 5, 3 from chapter 6. All right? And notice right here, they don't put the standard deviation of x bar, they actually put what it's equal to down here in the denominator. But it's the same thing. Okay? All right, guys. Have a good weekend. Happy 4th of July. We'll see you on Monday. And Haley has hours today, right? 3 to 5? Yeah. Yep. 3 to 5. Oh, if you need help on your homework, that's a good place to. Anybody. Yeah.
I'm late, but at least I'm consistent.
You're consistently late?
Yeah.
Thank you. What do you think, Crystal? Pretty easy?
Well, I'm worried about the one, I had to sit there and listen to your examples before I could do 6.2. And I don't know when I'm thinking.
And that one, 6.2 is just a lot of little, small, tedious steps.
I'm going to try.
You know, something that might be useful, I don't know how familiar you are with Excel.
I utilize Excel a lot.
So that, Excel would be very useful for that section.
I have actually, what I did is this.
But I didn't want to spend time training you on Excel to show you how to use it for this class, you know.
No, I did this because I didn't know how to figure these two, and I was utilizing Excel for it.
Oh,
But I
okay.
just printed this out so I
Yeah.
could write down directions. Only thing is I'm going to be driving all day today.
Oh.
And so I've made sure they've got internet access for me at the cabin. I said either you have internet access or I'm not going.
In
'cause-
Ruidoso or?
No, we're going to Arizona.
Oh, that's right,
Alpine.
Alpine, that's right.
But I was going to see possibly, because I don't know, we got to go home and pack, and then we're getting on the road. I'm going to attempt to make my phone a hotspot, but I don't think I'm going to be able to adequately work on 6.2 in the vehicle while we're driving.
Okay.
So first thing tomorrow morning, I told my husband, I said, I'm just not going to go fishing with you guys, but I'm still going to be late on that assignment.
Well,
I mean, I don't know how else to do it because I have to finish that one to go on.
Right.
I'm gonna try to do it in the car, but I doubt.
well, when you get to the cabin, I mean, I know it'll be late tonight, you probably won't really be in the mood for doing homework. That one I might actually go and move the due date.